All right, buckaroos and buckarettes. Why are you making that face, Mr. Madison? This is the metric, what do we call this? The metric checkup or whatever it is. Everybody needs to get this picture, okay? Now, what we're going to do here is what we're trying to learn is this system. We're not focusing on the metric system. We're just using the metric system as a tool. And the idea is that you're going to take the unit that you're given and put it on this end of this line, and the unit you want to convert to and put it on this end of this line, and then you're going to look for, hopefully, a one-step conversion factor, which would be an equality. In other words, whatever you have in the numerator would be equal to what you have in the denominator. How do you know what's in the numerator? It's the unit you're going to. So you're here, in this case, we have centimeters up here, meters down here. Now, this would be a piece of cake. How many centimeters per meter? Everybody who wants to know knows that it's 100. Why am I writing it in scientific notation? Because I want you to get used to scientific notation. 1 times 10 to the 2 equals 100. Okay? 1 meter. Excuse me. You could write this as 1 times 10 to the negative 2 meters, if you wanted to, per 1 centimeter. To me, it just makes more sense to leave the exponents positive. Okay? So, now what you have, the setup you have right here will convert any number of meters to centimeters regardless, an infinite number, right? Now you were given here 16.45. What I would like to see you do is convert this to scientific notation just out of practice, okay? So 16.45 is equal to 1.645 times 10 to the 1. 10 to the 1 is 10. Of course, 10 times this is 16.45. Now this makes it very simple. 1.645 multiplied by 1 is still going to be 1.645, okay? And now you're going to have the 10 to the 2 plus 10 to the 1. So this would be times 10 to the 1 plus 2. So your final answer would be 1.645 times 10 to the 3 centimeters. 1.645 times 10 to the 3 centimeters. Now, you know that there's 100 centimeters in a meter, right? So 16 meters will be 1,600 centimeters. So it's not the answer we're looking for. It's the system. This is the same thing as 16.45 centimeters. And if you wrote it like that, I accepted it. What I'm hoping you'll do is practice using this scientific notation and uncover any problems you might have now. Let's get rid of them. Let's solve these problems now, and then it won't be an issue when we get into talking about the number of grams. The number of atoms per gram and that sort of thing when we're really using huge numbers. Okay. But here again, number 2, same deal. Okay. We draw. We draw this straight line here. This straight line, and we're going to take the unit that we're given, which is milligrams, and we're going to convert it to the number we're looking for, or the unit we're looking for, which is grams. Okay, so our conversion factor will be grams over milligrams, and it's 1 gram per 1,000 milligrams, which is 10 to the 3. 10 to the 3 is 1,000, right? Milligrams will cancel. Now, for me, the easiest way to handle this is to convert this to scientific notation from the get-go, okay? And what you're going to do is you move this decimal place over 2 places, and that will give you 1.4. And because you made this larger by a factor of 100, then you will make this exponent smaller by a factor of 100. So what this will come out to then is 1.4 multiplied by 1 is 1.4, divided by 1 is 1.4, and it'll be 10 to the negative 2 minus 3. When you're dividing numbers that are raised to a power, you subtract the exponents. So this equals 1.4 times 10 to the negative 5 grams. Okay? The milligrams canceled here. Down here, number 3 is very similar. You're going from a smaller unit to a larger unit. I put the micrograms on here to make sure everybody understands micrograms. Micrograms is a little bit different unit. In other words, it's not an English letter, that's a Greek letter, microgram. It means a millionth of a gram. But your approach is exactly the same. Whether you know what a microgram is or not, you would still go this far, okay? So the unit here in the numerator is grams. The unit here is micrograms, and that's 1 gram per 1 times 10 to the 6 micrograms. All right? So here, there's nothing to do to this. We're going to leave this just like it's given to us, 3.54. You realize that equals 3.54 times 10 to the 0, because 10 to the 0 is 1. All right? So we're going to end up with 3.54 times 10 to the 0 minus 6. When you divide by that by that number raised to a power, you'll subtract the exponent. And so that comes out to 3.54 times 10 to the negative 6, and the unit here is grams. Okay? Now here we're going from a larger unit to a smaller unit. Okay? Again, so this one we're talking about liters to milliliters. Oops, not my straightest line there. Alright, so here we're looking at same system, exact same system. I'm hoping this system will become so automatic to you that it just is almost a automatic process for you. We're going from liters to milliliters, so we need a conversion factor that has milliliters per liter. And again, 1,000 milliliters to 1 liter. Same thing here. We had 1,000 milligrams to a gram, 1,000 milliliters to a liter. Milli is 1,000. Okay. Now, what do we have? We got 1.2, nice and easy, 2 significant figures, no problem. We know if we have 1.2 liters, we have 1.2 thousand milliliters. Okay. So it's really not a matter of, you know, having you do this for the sake of for the sake of doing the multiplication and the division and whatnot. It's a matter of having you lay out the system so that you're canceling units the way we want to cancel units. I showed you the other day that what we'll do when we're using a balanced chemical equation, we'll go from grams to moles of a reactant, and we'll go from moles of reactant to moles of a product, back to grams of a product, or pressure exerted by the product, or the volume of the product. So we're talking 5, 6, 7 steps. And you need a system to keep those steps straight for you and to cancel those units, keep those units straight. And this is what I highly recommend you do, okay? So we have this would be 1.2, multiplied by 1 is 1.2, okay? Divided by 1 is still 1.2, and it'll be times 10 to the 3 milliliters. 1.2 times 10 to the 3 milliliters, okay? Which should be 1,200. You only have 2 significant figures, so you don't put a decimal place there. Here we've got 10 to the negative, 10 to the negative 6, so this is going to be 1, 2, 3, 4, 5, 6. Okay, this would be 0.0000354 grams. That is what this number is telling you. This number is going to be 0.12345 grams, okay? These numbers are the same. And as you get, in the directions, I ask you to use scientific notation when you were more than 3 places from the decimal, just to get used to using it. Okie dokie? Alright, so let's see, let's go down here to the next page, number 5. Let's see, number 5 is here. Okay? 5, these, once you get this, once you see this, they're all pretty much the same, so you're going to use that line there, and you're going to take the unit that you're given, which is kilometers here, and you're going to convert kilometers to meters, and go ahead and just take it off, use the whole line if you need it. And the reason I get in the habit of using this whole line is because very soon we're going to be in multiple steps. Okay, So this will be meters per kilometer. There are 1,000 meters per 1 kilometer. And this number, again, we don't have to do anything. There's no scientific notation needed here. You realize that this equals 1.57 multiplied by 10 to the 0. So if you need to keep this straight in your mind, you can set this up like this to begin with. The kilometers will cancel as you divide them. So this will be 1.57 multiplied by 1 divided by 1 is still 1.57. And then you have the 10 to the 0 that you started with plus 3 here, and the units meters, and that comes out to 1.57 times 10 to the 3 meters, or 157 times 10 to the 3 meters, which is 1,570 meters. Okay. Now you notice we've got 3 significant figures here, 1.57, but if we're going to express it not in scientific notation, we've got to put that 0 there to tell whoever's looking at it that we're in the thousands, okay? Not the 157, it's 1,570. That's what that 0 is, but we can't use the decimal place because that 0 is not significant. Yes? So here we got a little bit different issue because we're adding. When you add and subtract these numbers, you are tracking the decimal place, okay? You are not necessarily watching the significant figures, or the 6 significant figures are dictated to you by the decimal place, not the total number of digits. So we've got 2.00 or 2.099 grams, and then 0.05681 grams, okay? So the issue here, the thing you're supposed to be aware of here is that we're here at the tenths, the hundredths, the thousandths place here. Here we have the tenths, the hundredths, the thousands, the 10,000s, and the hundreds of thousands, right? So we can't go beyond this thousandths place. We can't go beyond this third decimal place. That's what we're trying to get at here. This is not a test to see if you can add these numbers. It's do you understand that you can't go past this this thousandths place right here. So we add them up, and what do we get? 5, and that's 5, right? And that's 1, and that's 2. So we end up with 2.15581 grams, and we have to stop at the tenths place, so we have to stop here. Okay? Now because this next digit is 8, we're going to round that up. So this becomes 2.156, and the unit is grams. Okay? Now here we're talking about dividing these numbers that are raised to a power. Now in this case, you are counting the total number of significant digits. This value has 3 significant digits. This value has 4, so our answer can only be in 3. We have 3 significant digits here, 3 significant figures here, so we can only have 3 significant figures here. Okay? And when you do this division, when I slapped my calculator, it said 4.320987, and that was 10 to the negative 2. Okay? And the grams canceled, so we have to stop this at 3 significant figures. Okay? So that's going to be 4.32 times 10 to the negative 2, and the grams are gone. The grams have canceled here. Okay? Alright. So now we look here, and this is, I'll tell you what, let me switch this page right now. This is a simple density problem. Okay? And what we want to focus on here is the fact that this is a typical lab situation where you have in this case we're using a graduated cylinder, we're massing the graduated cylinder and the liquid in it. Well, in some cases you may just have a weighing dish, and so you take the mass of the dish and the substance in the dish, and you want to subtract the mass of the dish out. And you want to do that because you don't want to handle the chemicals. So you want to keep track of these keep track of the masses of the equipment that you're using, sometimes you'd have to take that out, right? But anyway, so what we have here is the 215.625 grams. Now that's the beaker and the water, okay? And so then we have the mass of the beaker is 110.4. And again, we've got tenths here, right? But up here in this balance, and this is kind of a funny situation because, you know, you would assume that you're using the same balance. But let's suppose this was given to you with these 5 significant figures, actually 6 significant figures, and you measure it here and you only have 4 significant figures. Well, when you do this subtraction, you can only go to this tenths place. Remember, this tenth was estimated, so you can't estimate out to the hundreds, okay? So you do this subtraction here, and you get 2, boom, what's that? 5 and 0.1, okay? So you're going to have to estimate this out. You can only go to the tenths place. So this mass would properly be recorded as 105.2 grams, okay? Now here you've got the simple density problem. Density equals mass over volume. Hopefully you would restate the situation there, and your mass is 105.2 grams, and your volume is given to you here as 114. Now here we've got 4 significant figures in the mass, and we only have 3 significant figures in the volume. So our answer can only be given in 3 significant figures, okay? And this comes out to 0.9228807, I believe is what I have, grams per cubic centimeter. Well, we can only go to 3 significant figures, so we're going to have to stop here at this thousandths, and this 8's going to dictate that it go up, so it becomes 9.23 grams per cubic centimeter. Okay, now here another simple density problem. These values are very similar to the ones you'll see in this density lab we're getting ready to do. So we've got the mass over the volume, and you want to restate that for a couple reasons. Number one, you're less likely to put these in the wrong arrangement, and number two, you will not forget the density value if you write it down every time you use it. But anyway, your mass here is 17.53 grams, and your volume is 6.47 milliliters, so this becomes easy, 6.47, and you divide this out and you come out to 2.7094 grams per milliliter. You have to round this to 3 significant figures, so it's going to be 2.71 grams per milliliter. Now your percent error, which we talked about, is equal to the experimental value, which is this. Oops, that's minus the accepted value, and we're not interested in whether it's a positive or negative value, so you can take the absolute value of it and divide it by the accepted value times 100. So that will come out to be 2.70 minus 2.71 divided by 2.70, and that equals 0.0371742, and I'm taking it on out there to show you that you don't want to throw your significant figures away yet, okay? You want to round one time after your last operation. So when we multiply this by 100, it's just going to move this decimal place over here between the 3 and the 7, and you're going to knock off, you're going to stop there with that third significant figure. So that becomes 3.72%. Okay? Now, on pages 55 and 56, there's a whole essay on this direct proportion and inverse proportion. Direct proportion says that as x gets larger, so does y. Over here we're talking about as x gets larger, y gets smaller, okay? So this is the inverse. B is the inverse. Okay, if you have any questions about any of those, you need to come see me and make sure you clear them up, because we're going to move on to using digits that are larger and smaller than this, so the scientific notation is going to get a little more complicated, and so are the steps. Okay? If you have any questions, come see me about it.